Here we are with another lesson from Math 8. Today we are working in Unit 3, Lesson 3. Today we're going to be talking about representing proportional relationships. We will talk about that with an equation, a graph, a table, as well as with the verbal description. Homework for this lesson is Lesson 3-3, Practice. And here we go. This is the page that you should be taken to, straight to page 330. In this lesson, we're going to we're going to graph the proportional relationships. To start out, we want to find some products of some numbers. We have the product of 15 and 2, 15 and 5/10, 15 and 25 hundredths, and then 15 and 2 and 25 hundredths. For this problem and for this lesson, I'll be switching back and forth to my document camera because I'm having trouble with actually being able to write on my screen. So here we go with our first problem. When we talk about 15 times 2, that might be some pretty simple mental math. 15 times 2, we know if we double that value, would be like saying 15 plus 15, which we know is 30. Now let's go the opposite route. Instead of adding 2, let's talk about multiplying by 5/10 or multiplying by a half. So we might think about this as 30 times 1/2, or we might think of half of 30. And half of 30, when we do that, is going to be 15. Now let's think about, whoops, just kidding. Not 30, that's from the first problem. Let's think about half of 15. Half of 15 would have to be 7 and 5/10. So now let's think about taking that even a step further. 25 hundredths we also know is 1/4. And so a fourth is like taking a half of a half. So if we take a half of 15 and got 7 and 5/10, and we take half of 7 and 5/10, what we would get is 3 and 75 hundredths. Now if we go on to the last one, talking about multiplying by 2 and 25 hundredths, we can think about these numbers separately. We've already multiplied by 2, and we've already multiplied by 1/4, or 25 hundredths. If we take those two values, 15 times 2 is 30, and then 15 times 1/4 is 3 and 75 hundredths, what we get is a total of 33 and 75 hundredths from 15 times 2 and 25 hundredths. That should get us going, get us thinking just a little bit to get into our work. As we get going into our work, what we need to understand is that each of these values were multiplied by the same value, which means that we're multiplying by what's called a constant rate. So as we talk about constant of proportionality today, I want you to understand that we have a new vocab word called constant rate. You may or may not have heard of this, but we'll see how that works out today in our lesson. So number one, here are two ways to represent the situation. As we look through, let's go ahead and switch back to this one. We have a couple of ways to represent a situation where we have Jada and Noah, and they're counting the number of steps that they take to walk a set distance. Now that distance is going to change, but we'll find out something does not in this situation. Noah counted the steps, when Jada counted, she took 8 steps, while Noah took 10 steps. Of course, this was in the same distance. And then they found that when Noah took 15 steps, Jada took 12 steps. So as we look at this is a ratio that's being compared for Noah to Jada, and Noah is 10 steps to every 8 steps of Jada, and then again, Noah 15 steps to every 12 steps of Jada. The way we're going to represent this is first off, we're going to start out with a table. But to understand that table, we have to understand the equation that's been given. To understand the equation, we really have to understand the variables. First thing is this: let x represent the number of steps that Jada takes. Whoops, I want to extend that a little bit more. So we need to understand that piece. Let's go ahead and highlight that. We'll give that one a yellow. And then let's talk about Noah and his steps. And Noah's steps will represent the y coordinate. So Jada's steps are the input, Noah's steps are the output. Now, how do we know where to put those things? When we look at a table is always going to follow an input and output. So as we look at this, the input is always going to be, the x-axis. Looks like my Okay, well, looks like we're doing something a little bit different. So in this case right here, this table, we would see that these are the x coordinates and these are the y coordinates. So as we build this, what we want to make sure that we do is everything that comes into the x column is only steps that Jada takes. We know that Jada took 8 steps, and then she took 12 steps. And then hopefully we can start to see a pattern developing. Well, if she took 8 steps and then 12 steps, then we see that there's a difference of 4 there, then logically we should see another 4 steps. We know that Noah took 10 steps to Jada's 8 steps, and then 15 to her 12. So under this case, we see that Noah is taking 5 steps in between, or that the distance and the change in distance is 5 steps. And so we can go ahead and look at that and make a prediction that since they're walking at constant speeds, that he's walking 20 steps to her 16. Now, with that information, we can actually look at these 4 values that are in this table, and we can make some predictions, but we can also talk about what's actually happening here. So what we're going to do is go ahead and switch back over here. The same table is written right here. And what we need to do with this table is we need to recognize something. Out of this table, we have at least 3 pairs of values. And within this table, we see that that's 8 to 10, or 10 steps to 8 steps, 15 to 12, 20 to 16. And you'll see and you'll notice that I'm going from y compared to x, because we know that y compared to x is the constant of proportionality. We have also learned that this equation, constant of proportionality, by multiplying by x on both sides of the equation, this expression, we get rid of x on the left and get the equation y equals kx. This is the equation that we need to start using every single time that we're going to build an equation. This is what we call our proportional relationship, or a formula for proportional relationships. In Algebra 1, it will be known to you as a direct variation. Now, how do we get 5/4 in? One way that we can look at this from the table is we look at the change in y. 10 to 15 is 5, so we see plus 5 here, and then we see again plus 5 here, while in the x we see adding 4 each time. And we know that our constant rate, our constant proportionality, is the comparison of y over x. So we can look at these directly and we can see that 10 eighths, 15 twelfths, 20 sixteenths, all of these values are proportional because they all equal to 5/4. And we want that simplified version to tell us that this value is our value for k. And that's what gave us our equation y equals 5/4 times x. Now the question is, how do I represent that on a coordinate plane or on a graph? We're going to go ahead and bring this over here to a graph to graph this relationship. We're going to have the equation. I'm just going to write it right here so we know where this is at. A couple of things can really help us out here. First off, we need to label our axes, because if we don't label the axes, then we can get really confused on what could happen. We know that the x-axis right here was supposed to be the number of steps that Jada took. So we're just going to call that Jada's steps. And then over here on the other side, this would be Noah's steps. So now that we know what our axes are, we can go ahead and start putting numbers to this. One way that we could think about this is each of these intervals right here, we get to decide what we are going to use based on the information that we're given. Since we had 8, 12, and 16 in our table, I think it would be appropriate to go ahead and go by 2s and call this one 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm just going to go out to 20. And then on our y-axis, we also had values that were going up by 10 or going up by 5s. So I think it would be very appropriate to go ahead and go 5, 10, 15, 20, 25. And this isn't the only way you can do it. That's the cool thing, is that you can use your intervals however you want to. At the end of the day, as long as the information is graphed correctly, we will see the same information. It wouldn't make sense to go ahead and put our intervals into the hundreds or into the 20s and use giant numbers like that, because we don't have great big numbers like that. It makes more sense to have numbers that are smaller and much easier to keep track of. So when we graph these points, we knew that we had 8, 10, and we had 12 and 15, and we had 16 and 20. And so we can go ahead and use those points and recognize that a pattern is starting to develop. If you look at these points, I'm sorry, that's really hard to see. It's shining off there. I've got one there, and one there. If you look at those points, we can see that a straight line is starting to occur. And if we follow that pattern back here to the left, then we see that we come back to the root of 0, 0, which is kind of cool. And since our friends here are walking at a constant speed, we can go ahead and connect these dots and graph as a line, because this is something that we're going to learn a little bit later, but not every single graph actually has a line. It's okay to have some graphs that don't have a line, that are just points. We will get to that as we go on. But what we need to make sure that we understand is that this data right here as a graph represents this equation right here, as well as this table. And the question in the next one is, how can you see or calculate the constant of proportionality in each of these representations? Well, when we think about the table, any x and y value that we're dealing with from this table is going to be y divided by x is equal to 5/4. That would just be our rule that we work with that one. When we go to the equation, we look at that and say, in our equation, as long as k is equal to 5/4, we are good. But our equation looks like this. Y is equal to 5/4 of x. When we go on and we look at the description, we can see that when we're talking about Noah as a ratio, Noah to Jada is going to be in this same format right here. That same thing is like saying y to x, or 5/4. And then finally, for every one step that Noah takes, we know that Jada is taking 1 1/4 steps, or 1 5/4. She just has a longer step. So that's one thing with this. When we look at part D and explain how you can tell the equation, the description, the graph, and the table all represent the same situation, we can look at this and see one major common thing is that all of them have a constant of proportionality equal to 5/4. Think about it. We talked about the table, the equation, we talked about the description, and we can even talk about that with the graph, that we see those same things. So kind of cool. Let's talk about our friends over at the Origami Club. This is on the next section that we're dealing with. Feel free to go ahead and fill everything out on here as you get going, since you don't have the paper. Friends at the Origami Club, what they're looking at is having a car wash, or a fundraiser that does a car wash. And we know that they're wanting to raise money for a trip, and they charge the same price for every single car. That's really, really important to note, because what this does is this gives us what we know as constant rate. So that's a big deal right there. So since it's a big deal, we'll go ahead and put it in that bright pink color to say, hey, pay attention to me. After 11 cars, they raised a total of $93.50, but after 23 cars, they raised a total of $195.50. Over here to the right, we see that there's a table that represents the same data. And then our job is to write the equation that represents this situation. But notice what they tell us here. We need to use C to represent the number of cars. We'll label that one. Maybe. Guess not. And then we need to use M to represent the amount of money. So let's remember that as we do this. Switching over here. To write that equation, we need to be able to know what K is first, or our constant of proportionality. In this case, our K is going to be the price per vehicle, because they're saying that they're charging the same price for vehicle. So we can find that a couple different ways. We can take our total of $93.50 and divide that by 11 cars. And that would be the exact same thing as $195.50 divided by 23 cars. I've already done the math a little bit earlier, but what I found out is that people are spending $8.50 per car. Both of these expressions simplify to 8 and 5/10. So I know that $8.50 per car is my value for K. So now I can go ahead and simply write that. Well, let's look at here, the number of cars. So if the number of cars is being multiplied by $8.50 to give us a total amount of money. And so now sometimes what I've found it helps with reading word problems or reading equations is rather than saying the letters M equals 8.5 times C, I found it a lot more helpful for me under a word context to say that the total amount of money earned or the total amount of money that's raised in dollars is equal to $8.50 per car that's washed. Helps for me. Let's see how this works out as far as the graph goes. Remember, the first thing that we need to do is we need to label the axes. If we're not sure exactly what to use, then I suggest go back to the table, because any good table is going to tell you what the input is and what the output is. And in this case, we know that X is going to be C, M is going to be the dollars, so we want to pay attention to those as well. Thankfully, here on the graph, they were given to us as M and C. So let's go ahead and label these. We have the number of cars, and then we have amount of money. Or we can say amount raised in dollars is probably more appropriate because of what it says right here on the paper. And now we need to just come up with proper and appropriate intervals. So the cars are going to come through one at a time. So I think just going by 1, 2, 3, 4, 5, 6, so on and so forth, I think that's a good idea. Also, the fact that we have two prime numbers right here might be a little bit more difficult. I don't want to do that again. So let's think about it along the top here. I think that it's probably more appropriate for us to go ahead and go, say, let's go by 20s. That's kind of nice because that actually ends at 200. If you're not sure about what intervals to use, feel free to go ahead and just count however many spaces there are right here. There are 10 spaces. Well, from top to bottom, there's 11. But if I look at just the ones below the arrow, there's 10 spaces there, and evenly distributing them out of there by 20s is a really good thing that you can do. And I say by 20s because I know that my big value with this is $195.50. Now, finding an exact intersection with this could be a little bit more difficult than we think it might be, but I think that what we can do is we can actually get really close on this one. And the really close way that we can do this is that we know that for every one car, it's $8.50, and for every two cars, it's going to be $17. So I could be thinking about those pieces. If I look at that $17 for two cars, that means that 20 cars will cost us $107, or will earn us $170. And so I could put a point way out here. If I'm not very sure about where that point is, that's a good spot to start, a good spot to estimate. 21 cars, maybe if we want to go with the table, we're getting pretty close to these values up here at the top. If I take away, a few cars in here, I really do. I guess what I'm trying to say is that it will get kind of difficult sometimes to be able to determine exactly where to put these points when we're dealing with numbers that are in decimal form. We can look at these numbers and we can think about other numbers to see how will they fit and how will they work in these situations. Like maybe if I take, I like the number 7. If I take 7 cars and I go ahead and I say M is equal to $8.50 times 7. Let's see what we come up with. If we take that value and we do, let's see if my calculator is going to pop up, $8.50 times 7 cars, $59.50. So if I do this ordered pair of 7, 59.50, that's really close to $60. So I can come here at 7 and just, I think because we have such a big stretch there, it's going to be right about there on that point. I can come along and take any others. So that tells me that 14 is probably pretty close to that same value, or going to be close to being right on that that intersection of two lines. So 14 times 8.5, $119. And I was right. So that one comes right about here. And what you'll notice here is these 3 points actually line up pretty darn straight. And then when I look at those and I bring them all the way back, they line up over here with 0, 0. And that tells me that's about where my line is. So kind of a cool way to get going. Good way to get started. But we have a complete graph with labels, with data, and with good intervals. Now, if we go back and we look at these things, how can you see or calculate a constant of proportionality in each representation? Let's go back to the equation that we found. In the equation, we see that in our constant of proportionality is 8.5, or 8.50, because we know that's the cost per car. In the table, again, we see that any x and y for y divided by x that equals 8.5, which we can take these ones, what we did at the very beginning, 93.50 divided by 11, 195.50 divided by 23. Both of them came out as 8.5. In the description that we're given, so right inside here, we see the same type of idea right here, where we could do the money raised in dollars per car. And we found that just by doing division. In the graph, we can say that we see this one by saying every coordinate and I'm going to tell you a new word, every coordinate pair, which is also known as a solution, is on the line every single time. So we always know that y divided by x is equal to 8.50, or y is equal to 8.5 of x. And again, that's our better equation that we want to follow. So how can you tell that the equation, description, and graph of the table all represent the same value? It all comes back to this again. Constant of proportionality of 8.5 is present in all. Every single one of them has the exact same constant of proportionality represented. It comes out here with the cost per car. It comes out here by taking y divided by x, comes out here in the equation, and it comes out here by seeing that constant rate. Every single point is on the graph. There's our big steps for this lesson. That's the big concepts and the big ideas. What we want to remember with this as we work through this is proportional relationships, is they can be represented in multiple ways. Which representation we choose is all dependent on its purpose. When we create a presentation for it, a representation for it, we can choose which helpful values help us to pay attention to the context. And so like for this one, I love this example in here. It says a stew recipe calls for 3 carrots and 2 potatoes. Well, that's kind of cool. What that means is that we have a ratio of 3 carrots to every 2 potatoes. And one way to represent this is with an equation. So we say that the number of carrots is always going to be equal to 3 over 2, or our ratio 3 to 2 of the potatoes. So it's going to be 1.5 potatoes for every carrot that we put in there. Now, if we want to make a large batch of this recipe for a FADME gathering, we're going to use 150 potatoes because, hey, why not? Math is the only place where somebody can buy 45 watermelons and nobody ever questions it. In this case, we're going to talk about 150 potatoes because we're going to make a huge pot of stew. When we talk about those potatoes, then we need to compare them to carrots, and we would just use this equation. If I want to know how many carrots I need, well, take 150 multiplied by 3/2, and then I know I need 225 carrots. Now let's talk about if we go to a restaurant and we want to make a little bit bigger batch. And those batches that we make every single time, we're going to say they use 300 potatoes at a time. Well, it might be helpful to see a graph or a table to be able to help us to quickly reference these values to make sure that whoever's making it doesn't have to work out an equation every time, but instead they can simply just look at the graphic and they can say, oh, if I need 100 or 300 potatoes, that means that I need 450 carrots. We could see likewise over here, they're saying, okay, if I have 150 potatoes, then I need 220 carrots, 300 potatoes, 450 carrots, so on and so forth. These representations, again, it all depends on the purpose. These might be posters that are on the wall, and this might be something that the bookkeeper keeps track of to know exactly how much money is being spent on carrots and potatoes in that restaurant. So different representations for different purposes. No matter what representation or what scale, if it's like a scale like this is used, that constant of proportionality, in this case 3/2, is always evident in each. The equation in the number we multiply by p. In the graph, we see it in the slope. In the table, it's the number we multiply by the values in the left column to get the right column. And then we can think of that constant proportionality as this, a rate of change. That rate of change means that something constant is happening and how we know what's going on with each term. So I hope this is helpful for you. I do appreciate you watching the video. Please make sure that you reach out to me with any questions and stay tuned for some homework help.